Hello everyone, welcome to my ME40058 homework free problem. So let's begin. The problem. So you are the lead investigator assigned to the theft of the Starry Night from the Museum of Modern Art. While the physical canvas is missing, your team has intercepted a corrupted digital replica suspected to be a carrier for a hidden message between the heist members. This investigation will require you to identify the culprits by extracting, analyzing, and applying image enhancement techniques learned in the course to solve the case. So in this problem, we're provided two images, which is the Starry Night, which is corrupted, and a surveillance plate image. This problem is made up of 7 problems or parts, and we will start with part A. So in part A, it asks us to load and display the corrupted Starry Night image, separate and show each RGB channel and display them, identify the hidden message, and determine which channel difference reveals the hidden message most clearly. Hint, try subtracting each channel. So in our first line of code, we're going to read the image or the image file and then convert the image into a double format. So then we're going to display the original image as it asks us to do, and then separate each channel. So since the digital image is made out of m times n times 3 arrays, we have the red channel, the blue channel, and the green channel here. We're going to display those 3 channels separately in this part of the code. Then in the last part, we're just calculating the channel differences, and we have the red minus green, red minus blue, and green minus blue here. And here are the results of the outputs. So the displays, this is the red channel, the green channel, and the blue channel. The red channel is definitely a lot darker than the blue channel here. And then we can also see in the next part of the line, we're going to display the channel differences, and then we determine which one it is just by visual inspection, and we end up determining that it is the red minus green here. And if you can see closely, that we can see there's a sort of a message on the corner here, but in red minus blue and green minus blue, it's kind of difficult to see because of the black background. Now in part B, based on the results of part A, using the best channel difference image, which we found was red minus green, apply and compare the following techniques. We want to contrast stretching using this function, histogram equalization using this function, and a logarithmic transformation. Determine which enhancement reveals the hidden message most clearly and identify the hidden message. So in the first line, we're using the contrast stretching using this function here, using the best difference, which we had assigned as red minus green. Then the histogram equalization using this function here, and then the logarithmic transformation is done in the next slide, where the constant scales the results so that the output stays within the displayable range. And we're using 1 divided by log, inside being 1 plus the max of the best difference. And then we're applying the log transformation in this slide, in this section. So it converts the image to a grayscale in the last line here. And then we're just going to display the different image processing techniques. So here are the results, and we can see this is just the red minus green image, then the contrast stretching, the histogram equalization, and the log transformation. And from these results, and just by comparison, we can see that possibly the log transformation has a bit of a better and clearer indication of what the message is actually saying. And it says 9 p.m. Gallery 7 or GAL 7, which is what we assume is the location and time that the heist members are meeting. So part C asks us to convert the corrupted image to grayscale and compute the 2D Fourier magnitude spectrum, the centered log spectrum using FFT shift, and the phase image. So in the code, we convert to grayscale first, and then we're going to compute the 2D fast Fourier transform on the grayscale image, and then shift the zero frequency component to the center of the spectrum. And then we're going to compute the magnitude spectrum by using the absolute function, and then compute the centered log magnitude spectrum using the log function with an absolute. And then we're going to compute the phase image using the angle function here with the F grayscale, fast Fourier transform grayscale 2D that we had calculated beforehand. And then we're going to display the Fourier magnitude center spectrum and the phase image next. And here we can see the results of the free images. So the 2D Fourier magnitude spectrum, the centered log spectrum, and the phase image. So part D asks us to identify the periodic interference patterns in the spectrum, apply a notch reject filter to neutralize the noise, then reconstruct the image using inverse FFT. Compare the original corrupted image and the filtered image. So we know that the notch reject filter will remove like specific unwanted frequencies that we kind of select in the images, and it's commonly used to reduce any periodic noise or interference. So in the code, we start off with the size of the grayscale image and then the frequency coordinate grids. We're gonna make the center, set the center, both the y and the x, and then we're gonna uh, do like start with an all pass filter. And then we have offsets, which are the coordinates of specific bright points that we select. And these are some of the coordinates I have found. And then this is just the notch radius. And we're gonna go through loop through each knot location. Calculate the actual notch center by adding the offset to the center of the frequency spectrum. Then we're going to compute the distance from every frequency coordinate to the current notch center, and then set all the frequencies within the notch radius to 0. This will remove all those selected frequency components and just it will look like it's blacked. And we'll see in the next slide that we applied a notch reject filter with this equation. F shifted times by the h, and then we're going to reconstruct the image by shifting the filtered spectrum back to its original Fourier arrangement with the IFFT shift function. Then we're going to convert the filtered image back to the spatial domain using the inverse FFT. So then we're going to rescale the filtered image just for the display. And then we're going to display those filters and the results. So here we can see the original corrected grayscale, and then these are the filtered points that we had selected and the coordinates. And then this is the filtered image. And we can see that the filtered image does not provide us a more detailed message, like idea of what the message is. And so what we had done previously actually worked better than filtering out all the noise here. So for part E, it asks us to use the hidden address recovered in part D. Investigators retrieved a degraded surveillance camera image of the getaway vehicle. Apply the following techniques to improve the image quality of the vehicle's license plate using Gaussian filtering and median filtering. So then compare the results. So in the code, we're reading in the license plate image first and then converting to grayscale if it's RGB. Then we're going to convert it to a double format. Then apply the Gaussian filtering to smooth the image using 1.2, as larger values kind of gave more of a stronger smoothing that was not really necessary. Then we're going to apply the median filtering and then display those two images. And then the best results turned out to be the median filtering. So you can see here that the original surveillance image is really bad, but then with the Gaussian filter and median filter, it kind of smoothed out all this kind of specks in a way. But I would say the median filter looks a little bit more smoother compared to the Gaussian filter, although they are very similar. So for part F, it asks us to use the best results from part E and apply the following enhancement techniques to improve the readability of the plate, so specifically more sharpening. And here we use the Laplacian sharpening, and using the same parameters as in the lecture. We're going to sharpen the image and by subtracting the Laplacian response. Then we're going to use the unsharp masking. We're going to create a Gaussian low pass filter to create a blurred image. So the parameters are identical to the ones in the lecture here. And then after creating the blurred image, we're gonna create the unsharp mask by subtracting the blurred image from the best filtered image. Then we're gonna add the scaled mask back to the original image. 1.8 is chosen after testing the best amount of sharpening. Then we're gonna display all the images next. Here are the results. So this is the original, the Laplacian, and the unsharp masking. And we can see that the unsharp masking kind of gives more detail as to what the letters are and the characters. And the last question or part is G. Based on the improved and for surveillance image from part F, what is the vehicle's license plate number? And we can get that it's 7KQ3142. Thank you for listening to my presentation.